Hi, welcome to term 2. We're starting this term in week 3, and we're going to start looking at area under curves. So by now we would have done a bit of integration. We've worked out the difference between the definite and the indefinite integral, and hopefully you have an understanding that the definite integral gives us the area under a curve between 2 points and the x-axis. We've also looked at the properties of integrals, and you should be aware that the area above the x-axis will have a positive area. Area below, or the integrals taken below the x-axis, so between the curve and the x-axis, below the x-axis, will be negative. And so when we are finding or using integrals to find area between curves or area under curves, we need to be aware that curves can dip above and below the x-axis, and so we need to treat the areas above the x-axis different to the way we treat the area below the x-axis, because as we know, the area above the x-axis under a curve, between the curve and the x-axis, is positive. Area underneath is going to be negative. So we need to take that into consideration. We only ever deal with positive area, so we need to make an allowance for that area under the curve, under the x-axis. So if we look at a curve such as this one here, where it's both above and below the x-axis, we need to calculate the area above the x-axis first, and then we calculate the area below the x-axis separately. So in this case, we're looking at the integral if we're looking at the area from a to c, we need to find out the area from a to b. So work out the integral of this function from a to b, and then we work out the integral from b to c. It gives us the area. Now this is going to be a negative value, so what we need to be aware of this is going to give us a negative one, so we use the absolute values. So we take away the negative sign and just add the values up with no regard to the sign in front of the area. So we should be familiar by now with calculating definite integrals, and if we look at an example now, we want to find the area enclosed by a function y equals x squared minus 3x minus 4 between x equals 2 and x equals 5, and the x-axis, or where y equals 0. Now with these questions, the best thing to do is to put it into your graphics calculator or a graphing tool and work out what the curve actually looks like between these 2 points. So if we do that, this is what it looks like. From 2 till 4, we have a value below the x-axis. From 4 to 5, we are above the axis. So we need to calculate these two areas separately. So even though we're going to find the total area from x equals 2 to x equals 5, we need to break that up into two calculations: the integral from x equals 2 to x equals 4, and the integral from x equals 4 to x equals 5. So it's just basically what we said. And so we're going to work out those two areas, and then our total area between the curve and the x-axis is going to be those two areas added together. So once we've determined where our integrals lie, this should be fairly familiar to us all by now. We're going to find area 1 is the integral from 2 to 4 of x squared minus 3x minus 4. We do the integral on that, we get x cubed minus 3 minus 3x squared divided by 2 minus 4x between 4 and 2, do our substitutions, calculate the area, and we get an area of negative 22 divided by 3, which is what we expect because it's below the x-axis. So that's our first area. Similarly, we calculate the second area from x equals 4 to x equals 5, do our integral, substitute our values, and we get the area is 17 divided by 6. And again, that's positive, it's above the x-axis, so it's what we would expect. So we've got our two areas. What we're interested now in, we ignore that negative sign on the first one, we just think in terms of absolute values. So 22 divided by 3 plus 17 over 6 gives us 10.167 units square. Okay, so we're using integration, the definite integral, to calculate the area under a curve between 2 points. If we look at another example, finding the area enclosed by 24 minus 2x squared and the x-axis. Here we're not given any limits, but as soon as we graph it, we'll see we've got our zeros here. So the area enclosed by this curve and the x-axis is this shape here. So it's going to be between x equals -4 and x equals 3. Again, you should all know how to calculate the zeros from a quadratic, but we're not really interested in that at the moment. What we're interested in is what this graph looks like. So just put this graph, or this function, into your graphics calculator, calculate the zeros, and then just proceed from there as you would with any integration problem. So find the x-intercepts either graphically or algebraically. Obviously it'd be much more quicker to do it graphically. And so what we find, we're looking at the area, or the area is given by the definite integral between x equals -4 and 3. So again, that's where our x-intercepts are, and the function 24 minus 2x squared. So if we do our integration, 24x minus x squared minus 2/3 x cubed, do our substitutions in, we get the area to be 343 divided by 3. So that is how we calculate the area under curves. Just in summary, remember the area below is going to give us a negative value. When we do the integral, if the area between the curve and the x-axis is below the x-axis, that's going to give us a negative value, or a negative definite integral. Above the x-axis is going to give us a positive definite integral. And when we're calculating the total area, we're looking at the absolute values of those two areas. So we ignore the negative for the area that's underneath the x-axis, add those two values together. Obviously, if it continued repeating it in like a sinusoidal fashion, every time you had a negative area, you would find the absolute value of the area and add it to the area above. If all our calculations are dealing with area under the curve, again, it's going to give us a negative integral, so we just ignore that and use the absolute value.